Okay, so this is my 6.3 numerical model presentation. Just before starting, I need to state that all the definitions throughout this presentation were gathered from the John Honeyborn and Sarah Powell's OCR A-Level PE textbooks, both Year 1 and 2. So, a numerical model. So the term numerical model is very generic in that this model looks at all kinds of things, be it angles on the body or certain forces being generated during an activity. Or certain movements. There is no one set piece of information that this model looks at. However, the data it uses is quantitative, often in graph form. A lot like the technical model, this model is often created through and compared to literature, elite performers, and/or the combination approach. Here they may look at the average reaction force generated by an elite basketball player when jumping for anything from a layup to box out and rebound. When doing so, they may measure ground reaction force, like we've done, the gold standard body angles on the individual, and then compare this to other literature to get an idea of elitist force outputs and optimal body angles when performing certain skills. This is done using kinetics and kinematics. So kinetics looks at the forces involved in the movement of a body or object, be it linear, so force, gravity, mass and weight, or angular, such as torque and levers. Whereas kinematics is the study of motion and change in position of a body or object, and this looks at things such as linear motion, curvilinear motion, angular motion and general motion, which we will talk about later. So, for this model, we used a force plate and 2D video analysis as our technical model analysis. But in order to actually carry out this model, there's a specific methodology that must be followed. So first of all, a PAR-Q must be completed, including an informed consent sheet to be read and signed before beginning. All protocols throughout the entire session have to be explained thoroughly to everyone, and this should then be followed by a standardised warm-up for every participant before their testing in order to increase the validity of results. Following this, the plate is then calibrated whilst the performer stood on it to zero in their weight. The individual should be made familiar with the jump angles well before this, so 135 degrees, 90 degrees in our case, which is close to that of a box out and rebound. This is done using a goniometer to show the exact angle at the knee joint that is required and help develop a feel for that angle. Then the subject should stand on the plate for 1 second to create a constant on the force time graph, and they will then be counted down before they jump. The jump itself was static and in upwards motion. This should be done 3 times, and an average reading was then taken of the 3 jumps. So in this case we were using a Kistler force platform to measure ground reaction force with a sampling frequency of 1000 Hz, all to increase reliability and validity of our results and testing. Obviously, using the average score, making an average, also helps with validity and reliability. So from this, a force time graph was generated showing the unweighting phase, the braking phase and propulsion phase from the performer. But we can also see the amortization phase here, showing us the time taken between concentric and eccentric contraction of the quadricep muscles, indicating the overall strength of the area and speed of contraction, ability to contract quickly, but also the functionality of the Golgi tendon organ to help indicate training ideas and areas to work on with the performer. So it might be that this organ needs to be desensitized to allow for greater range of motion. So the entire process will be recorded for the purpose of 2D imaging. The use of 3D Vicon cameras and software would have been much more useful for analysis, as this would have allowed to see the exact movement through the body over the jump and give much deeper analysis of the joints, the motion and the body angles, the body movements. Anyway. With the use of 2D imaging, it was crucial that slow motion cameras were in use, as we needed to be able to film around 1000 frames per second. This of course means using a high shutter speed to capture the finer details. High shutter speeds bring the risk of lighting problems and can cause the resultant film and captured footage to be poor and have reduced visibility. So this can also cause a problem when actually trying to view the end picture or recording. So when setting up the camera, there are many factors that must be seen to prevent the footage from being invalid and to prevent any perspective error. So triangulation must be perfect, with a full width of view to see every set piece of motion from the subject. Pan must remain level across the entire area of motion, as must tilt. Tilt must remain perpendicular to the point of analysis. It needs to be dead level. Vertical reference and horizontal scaling should be used. This can be done with a meter stick being held close to the performer in order to tell the computer where the meter point is. The plane of movement must be considered. Luckily the jump was only on a sagittal plane, making it quite simple to film. Only one angle was really needed. However, any movement taking place over multiple planes will require multiple camera angles, making the setup much more difficult, meaning you most likely need more than one camera. Roll must also be considered. There must be no roll when recording the jump, otherwise perspective error of the jump angle may be incorrect. There may be perspective error of the jump angle. So what's 90 degrees could look more like 85 degrees or 100 degrees, all depending on the angles. And yeah, this must be correct from the jump through to the landing. The field of view must also be maximised so that every area of the body is within the frame at all times, from the jump through to landing. So all in all, any small detail that is incorrect with the camera will most likely cause huge perspective errors, which will lead to any data collected being completely invalid and will be a call for retesting, which will obviously be quite a strenuous process. A higher quality data collection means a higher quality level of data analysis. So forces. There are 4 forms of force: internal, external, horizontal and vertical. You could technically argue 6 if you're not talking about balanced and unbalanced forces, but they're more of a term. So all of which are very prominent in a basketball game. All motion is created by force, and a force is a push or pull that isn't visible but you can see its effect. A force acts on an object, so a force is exerted onto a body, and force is also a vector, so it's measured in magnitude, so size and direction are both required. Forces can be applied with or without contact, and within this model we'll be looking predominantly at impulse, predominantly at these following forces. So impulse, which is concerned with the length of time a force is applied to an object or body, and relates to the change in momentum as a result. For example, how long the foot of the player applies a downward force to the ground when taking off for a layup. We'll also be looking at momentum, which is the quantity of motion possessed by a moving body. An example would be the motion gained by a player as he runs down the court. We'll also look at acceleration and mass. So acceleration equals force divided by mass. It's the rate of change in velocity, and force is mass times acceleration. So mass is a constant throughout sport, so in order to change acceleration, the magnitude of the force applied must be changed. An unbalanced force must be created in order to cause acceleration, whereas a balanced force would cause no change in rest or motion. So here we'll discuss the types of force and the effects it has. So firstly we have internal force. This force is generated through muscular contraction. For example, the contraction of the quadricep muscles and the upward drive of a layup. Then we have external force. These are forces that are present outside of the body and act upon it, such as... then we have external force, forces that are present outside of the body and act upon it, such as applied force, air resistance, gravity, weight, drag, and friction. External forces can then be classified as either horizontal or vertical. So horizontal forces are things such as friction, found between the player's trainer and court when in motion. It's the force that opposes the motion of 2 surfaces in contact. Then we have air resistance, which is present against the player's body when moving forwards. It is the force that opposes motion through the air. Given that the basketballer is indoors, air resistance remains relatively constant, and friction unbalances very easily. meaning it is much easier to gain greater amounts of acceleration when indoors. Then we have vertical forces, so in this case weight, reaction force and gravity. All of these are hugely present in basketball, as there is frequent points in which the individual will be in upwards motion from the ground. These forces will be acted upon them very regularly throughout this. We also have direct forces. These are forces that are applied straight through the centre of mass, such as gravity and weight, whereas eccentric forces are forces that act outside of the centre of mass and result in angular motion. So if a basketball is struck outside of its centre of mass, it will cause it to spin, whereas if hit dead on, it will travel very straight. In basketball, balanced horizontal forces are present between the performer and opponent when this is in the preparation phase of a box out and rebound. So yeah, horizontal balanced forces between the opponent and player. This is in the preparation phase. Yes, so also in the preparation phase of box out rebound, there are balanced vertical forces, so between the performer and the ground. There's very little movement going on, no upwards movements or anything. It's all very much quite level. But then in the execution phase, there's an unbalanced horizontal force between the performer and opponent, in that it's likely that one or the other is going to be pushing a lot more against each other, so one will be pushing harder than the other, creating unbalance between those two, and also an unbalanced vertical force between the performer and the ground as he jumps to receive the ball off the rebound. The ground's remaining stationary, but the performer is able to move. So there are 5 main effects that force can have. First of all, it can change a body's shape. So when a player applies a direct force to a ball in a block, both the ball and shape of the player's hand will temporarily change to cater for the resultant force of the block. Secondly, it can cause a change in direction of travel. If a ball is blocked whilst moving forwards, it may end up veering to the side or moving backwards. Thirdly, force can cause rest to motion, so can put things into motion. So, for example, in the toss-up start of the game, the player applies force to the ground in order to jump upwards from static position to reach the ball. They go from rest to upwards motion. Force can cause acceleration. So when a player applies a high level of force to the ground, they can accelerate down the wing to move up the court. And lastly, force can cause deceleration to occur. When the ball hits the backboard after a shot, it tends to decelerate due to the reaction force between the ball and board, causing its overall level of motion to lower. So yeah, as stated previously, there are 4 main types of motion: linear, angular, projectile, and general. Linear motion is the movement of a body in a straight or curved line, where all parts move the same distance in the same direction over the same time. For example, the upwards phase of the layup. The performer's body in general is moving upwards over the same time in the same path. Angular motion is the movement of a body or part of a body in a circular path about an axis of rotation. So the rotation of the ball as it travels from a 2-point shot, possibly. Projectile motion is the movement of a body through the air, following a curved flight path under the force of gravity. So an example of this might be the movement of the ball after a chest pass across the court. And general motion occurs when multiple forms of motion are acting upon the body at once. For example, a player making an evasive run down the court, incorporating spins and other manoeuvres to evade players. So there'll be lots of different forms of motion here. Here we talk about Newton's 3 laws of motion. So firstly, we have N1 inertia. So this states that a body will continue in a state of rest or uniform velocity unless acted upon by an external force. In other words, it's the body's resistance to a change in velocity. With this model, inertia is the most prevalent law of motion that we end up looking at, as it is present in all areas of basketball, be it the starting jump for the ball from standing still to jumping, or the explosive jump in the execution phase of a box-out rebound, where the individual must change their state of velocity to a much higher rate, or even the blocking of the ball in an opposing shot. The ball is forced to change both its direction and rate of velocity, so inertia is always to be overcome during a basketball game. And then N2, Newton's second law, is acceleration. This is stated as being the body's rate of change in momentum in proportion to the size of the force applied, travelling in direction, and it travels